But what Newton is imagining is that behind all that, behind all those imperfect representations of time, that there must be a perfect one. So there must be this sort of abstract thing just in metaphysically sort of behind the universe that dictates time. So this is his definition. It sounds perhaps a little bit like common sense, especially if you live in a world where clocks have been ticking away for 600 or 700 years. But there are problems with it. And so right after he came up with this definition, some of his colleagues in Germany and elsewhere objected. They said, can time really be measured other than in relation to the motion of objects? So this is an interesting question. Newton says yes, because he believes there's an absolute time that just is independent of everything else. But people like Leibniz, who call themselves relationists, say, no, it doesn't make any sense. You've got to have objects first. You've got to have matter first. If you have matter in motion, then you can look at that and you can say, aha, I deduce that time has been passing. But what if there was no matter? What if there were no objects moving? How would you know time was passing? Now, it's hard. I know this is a little bit challenging, because if there's no matter, then I guess you're not there either. So it's complicated. But nonetheless, this was a real argument that these guys had, and not the last one either. They ended up, of course, bickering about who invented calculus and stuff like that. Other things they like to argue about was time passing before God created the universe. This is a very peculiar sounding question in the 21st century, but it was very much an urgent question back then. Everybody involved in these arguments was a Christian believer of one kind or another, although it's worth mentioning that Newton's beliefs were very unorthodox. He denied the Holy Trinity, so he thought there was just sort of one God, which sounds sort of harmless enough, but if your employer is Trinity College, you have to, you can't deny the Holy Trinity. It was actually a criminal offense in Newton's time in England. So a lot of his theological writings, of which there were mountains of them, he kept them secret. And in fact, a lot of them were never published until much more recent times. So we have this question, if time is just going to infinity in both directions, then what's going on? You've got a God who's creating the universe. These people took the Bible literally, so there's a creation event. But what was going on before that? Is God just kind of sitting around and waiting for the right moment? So this is an objection, and Newton is aware of it. And he doesn't really have much of a comeback other than to say that, well, God is God, so he can do whatever he feels like, and if he wants to wait, he can wait. One critique of this that I read from some professor writing just a couple of decades ago, I guess a philosopher, compared it to the idea of a student getting out of bed. If it's a weekday, you have to get out of bed because you have to go to class. If it's the weekend, you don't have to get out of bed. But you still eventually get out of bed. It's just that, you can do it whenever you feel like it, right? So maybe it was something similar in the case of God creating the universe. So again, Newton doesn't have a problem with this, but Leibniz believes it's just a very sort of bizarre philosophical situation that Newton has gotten himself into here with his definition. He suggests that maybe it's more logical that God created time together with the universe, which is not a new idea. That goes back at least to Augustine, the early very early Christian thinker. And of course it continues today in a slightly different form, but this sort of debate about what was going on before the Big Bang very much has its philosophical roots in these arguments that Leibniz and Newton were having. Now, I'm skipping over a bunch of topics, and so I show this slide just to give you a hint of the things that I'm not saying, and it's a preventative measure. It's because I don't want you to think, well, he didn't mention the second law of thermodynamics. What? Maybe he's not familiar with the second law. So I just want you to, just be assured that there is other stuff that I could have talked about, but I just can't today because time doesn't permit. But I want to talk about Einstein, who comes up with his theory of relativity in two parts, special relativity and general relativity. And some of you have taken physics classes, so you know a bit about these, or you've perhaps done some reading on your own. Both parts of the theory are a refinement of what Newton had said about the nature of space and time and matter and energy. Special relativity involves corrections that have to be made to Newton's equations when things are moving very quickly, when things are moving near the speed of light. And general relativity, which is the theory of gravity, is a refinement of Newton's law of gravity that becomes important when there are very strong gravitational fields, as there would be near a black hole, or as there would have been in the early moments of the universe. This is not a complete list, but this is a partial list of some of the weird implications of Einstein's theory. Things that we now know are definitely true, but all of which would have been quite surprising or shocking to Newton if you were aware of them. Space and time become linked in this four-dimensional entity called space-time. That is novel, but what's novel is the way they're linked. It's actually not a shock that they're connected, because it's actually impossible to have a conversation about space without mentioning time, and vice versa, right? If someone asks you, how far is it to the mall, and you say it's 5 minutes away, well, okay, so like, what have you done? You just described a distance in terms of time. Well, yeah, you assume there was a velocity and whatever, but there is obviously a link, right? But what Einstein did is show just what the nature of that link was and how surprisingly intertwined space and time actually were. Measurements of time depend on the speed. Well, now that's a bit of a shock, isn't it? Because in Newton's world, time is absolute. So any two people anywhere measuring anything are always going to have the same answer. But Einstein showed that's not the case. Twins ending up with different ages, this always strikes people as being quite shocking, but it can happen. And yeah, it's just, again, well, I'll talk a bit more about it. It's because everybody more or less has their own time. There is no more master clock for the universe. And gravity destroying space-time, I don't know if you saw the PBS series with Brian Greene on, the Elegant Universe, but you've probably heard some of these ideas. And this is a feature that, of course, would not have existed in Newton's world. I'll try to help us picture four-dimensional space-time. You have to use certain tricks because you can't really picture a four-dimensional entity, but you can sort of strip off some dimensions, which kind of is a useful trick. So take the Earth going around the Sun. Now that's three-dimensional in the sense that the Earth is a solid body and the Sun is a solid body. But you can sort of pretend it's two-dimensional, pretend that the Earth's orbit around the Sun is just a frisbee or a pancake, so you've got that down to 2 dimensions. And here's your X and Y axes for space. Now, of course, really space is three-dimensional, so it would be X, Y, and Z, right? But we can cheat. We can take away the Z because we don't need it, and then we can replace it. We can use the vertical axis for time instead of space. And again, for those of you who are sort of physics buffs, you've probably seen diagrams like, so you know what's coming next. What's coming next is that you let the system evolve in time. So you've got an object moving in space, but also evolving in time. And this is just really nothing more than a trick. It's just a way to picture time and space together as this four-dimensional thing that we call space-time. And if you want to give these things names, we call them world lines. So the Earth has a world line, the Sun has a world line. You have to choose your reference frames carefully. This is the reference frame in which the Sun is just standing there. Of course, you could have a reference frame centered on the center of the galaxy, in which case both the Sun and the Earth are moving around, and so on. In everyday life, we usually just pick a reference frame where the Earth is stationary, and then you have a world line as you move around through the Earth. Another funny implication of Einstein's theory, which I've hinted at already. There's no absolute simultaneity. This is quite a change, because in Newton's world, something happens here and something happens here. They're either simultaneous or they aren't. So if they are, let's say, simultaneous, in Newton's world, there can only be universal agreement from everybody everywhere as to whether they were simultaneous or not. But that breaks down for kind of complicated reasons. I mean, there is a thought experiment involving a train that basically anyone can follow, but I don't have time to go through it. But this is one of the weird things.